So this week's tutorial is basically based on your lecture example, right? It is somewhat, actually everything is similar, only the values of the current is different, that is 0.7 milliamps, and our R value over here is different, right? That is 10 kilo ohms rather than 20. The rest of the question remains as it is. So I'm just directly using the lecture slide solution to discuss the solutions for this week's tutorial, right? In between, I have made some editing. So just because of this particular changes in the values have caused the solution to change. Uh, so let's go over the tutorial. So this week's tutorial is just based on only one question, that is basically on the differential amplifier. So let's go over that. Given differential amplifier in the figure, right? So this is the differential amplifier that is given in the figure, right? Or in your tutorial, right? This is the same. All four transistors are matched. Take beta is equal to 200, right? A, choose the value of R to give the source current I is equal to 0.7 milliamps, right? It is 0.7 milliamps. Next, take this value of R, right? What is the output voltage of the circuit when V in 1 is equal to V in 2? And all transistors are active. So basically we have to identify our R and we have to identify the output voltage for this particular question. So in order to calculate our output voltage, right, if you go back to this particular figure over here, this particular circuit over here, right, this particular circuit over here is actually the one that I have just circled is actually mirror circuit, right? So I'll erase that now. So that is a mirror circuit, right? So in a mirror circuit, what happens is whatever current is actually flowing on one side of the one side of the mirror circuit is actually reflected on the other side as well. So whatever I value we have over here is also the same I value that we have over here, right? So remember our I value is 0.7 milliamps, right, at the moment. So our I value is 0.7 milliamps. Now, knowing that this particular node, the voltage at this particular node is going to be negative 10. Remember, it is going to be negative 10, right? So just because of this negative terminal being attached to this particular node, we can say this the voltage at this particular point is going to be negative 10. Now, we know that there was a voltage drop over here of minus 0.7 volt, right? So a voltage drop of 0.7 volt. So the voltage over here will be, if you walk backwards, so whatever node voltage we have over here, we add this voltage drop that was 0.7 volt. So we add 0.7 to that. So minus 10 plus 0.7 volt is going to give me minus 9.3 volts. So the voltage at this particular node or at this particular point is minus 9.3 volt, right? So since this particular branch is shorted, so whatever voltage we have, it is the same voltage that we will be having at this particular node as well, right? So this forms one node. Okay. So whatever voltage we have is reflected at this particular point. So the voltage, the voltage at this particular point is zero, right? Since it is grounded, so it is zero. So the current basically flows from high voltage to low voltage. So if we write the branch equation or the nodal equation for this particular branch, it is going to be the current in this particular branch is basically equal to the high voltage. So high voltage in this particular case, since the current is flowing from in this particular branch, so this particular terminal will be having the high voltage. So it is zero minus 9. It is 0 minus whatever voltage we had at this particular node divided by resistance. So basically, if we take the voltage at this particular node as VB3, so the current equation for this particular branch is going to be I is equal to 0 minus VB3 divided by R. And then we can solve for R. Remember, I value is 0.7 milliamps, right? And our VB3 value is minus 9.3 volt. So knowing these two values, substituting it into this particular question and solving for our R value becomes, our R value actually becomes 13.3 kilo ohms. Okay. So I hope all of you got 13.3 kilo ohms, right? Next is we have to solve for our V out, right? So solving for our V out, right? We know that as per the question, it says we have to find the V out when V in 1 and V in 2 is equal, are both equivalent, right? Or we have a equivalent input. So in that particular case, V in 1 is equal to V in 2. So in that particular case, whatever V in you have in this particular branch, it is the same in this particular branch, right? So overall circuit is actually balanced out, right? So overall, this differential amplifier is balanced out. So in that particular case, whatever IC value you have over in this particular transistor is also equivalent to the IC value in this particular transistor, right? So knowing that, so our IC1 is basically equal to IC2, right? Which is equal to, if our beta value is 200, if we solve for alpha, or we can assume that alpha is equal to 1, right? Directly, if our alpha value is not given, we can assume alpha value is equal to 1, right? Usually it is 1, right? Unless until given. So usually it is around 1. So even if you solve using the formula for alpha, you'll still get alpha value is equivalent to 1, right? Using this beta value. So in that particular case, we'll assume alpha is equal to 1 directly, right? So in that particular case, whatever IC value you have, it is the same as our IE values, right? So IC1 is basically equivalent to IE1, and IC2 is equal to equivalent to IC2. Since both the sides are symmetrical or identical, what happens is whatever current is you have, the emitter current you have from this junction, and whatever emitter current you have from this particular junction adds up at this particular node, right? So we get I, and we know our I1 and I2 is going to be equivalent because the circuit is balanced, right? So basically whatever current we have over here is due to this IE1 and IE2. So in that particular case, IE1, right, is basically, or the emitter current for one of these transistors is basically half of this I, right? So whatever IC value you have, whatever emitter current you have is also equivalent to your collector current, right? Since our alpha value is equal to 1. So in that particular case, our IC1 is equal to IC2 is equal to I divided by 2, right? So our I value is 0.7 milliamps. So divided by 2 is going to give us 0.35 milliamps. Then V out is equal to, we have to find our V out, right? Definitely, we have to find our V out. I forgot about it, right? So V out is at this particular point. So if we write the Kirchhoff's law, or if we write the loop equation for this particular branch over here as well, our V out is basically equal to, right, the VCC. So VCC minus I times R, right? VCC minus I times R is this particular junction. So that is going to be basically our VCC. Our VCC is positive 10 volts. So 10 minus I times RC. So I value is IC2 is basically equivalent to IC1, which is equal to 0.35 milliamps, right? So IC2 times 10 kilo ohms, right? Remember in your question, it is 10. In the lecture slide, it is 10, 20 kilo ohms, right? So we'll be using 10. So IC2 times 10 kilo ohms is equal to, right? If you evaluate using this I value, that is 0.35 milliamps. So this particular equation will become 10 minus 0.35 milliamps times 10 kilo ohms is going to give us the output voltage as 6.5 volt, right? Okay, is that clear? Is that clear? Okay, so you get that solution, right? Isn't it? Okay, so moving on to the second part of this question, it says show that we have to show this particular part, right? That basically our V out is equal to this, right? So there's an error. Remember, this cannot be same. The V out equation cannot be same for this the question that is given in your lecture slide as to the one given in your tutorial, because the values are different now. Okay. So there was an error in this particular question. However, we'll ignore this and we'll try to solve for V out, right? We'll write an equation for V out, right? So we can ignore this, right? Because our I times RC value is going to be different. So that is one, right? You might have experienced this. So there's an error. You might not be able to solve for this particular equation. Yeah. So basically, we cannot solve. So we are just deriving the equation, the V out equation. So basically, our IC1 is equal to saturation current multiplied by the exponential of V in 1 minus VE divided by VT. So similarly, our IC2 is going to be same, right? The same equation, just in place of V in 1, we'll be using V in 2. Now, using these two equations, we can see that our IC1 divided by IC2 is equal to exponential of VIT divided by VT. Now, knowing that I is equal to IC1 plus IC2, right? We can derive our I value in terms of IC2. So that is basically going to give us IC2 into 1 plus e to the power of VIT divided by VT, right? Okay. So once we have this equation, right? So I believe you have solved this in your lecture slides, right? So that is why I'm not elaborating more on this particular section at the moment. So whatever value you get for your I, you write the equation for your V out. So V out is basically equal to VCC minus IC2 times RC. Remember our IC2, we can make IC2 the subject of the formula over here. So basically that will be I divided by this whole term over here. So taking whatever we get from this, so whatever IC2 is equal to from this particular equation, we take that IC2 value and substitute it over here. So in that particular case, it will be I divided by 1 plus e to the power of VIT divided by VT is equal to IC2. So we take this particular term and substitute it in place of IC2. So we get our VC2, we get our V out equal to VCC minus I times RC divided by 1 plus e to the power of VIT divided by VT. Okay. So now we know our VCC is equal to 10 volts. Okay. We know our VCC is equal to 10 volts. So our I times RC value is going to be equal to, remember our RC value is 10K and our RC value is 10K and our I value is 0.7 million. So 0.7 million times 10K is going to give us 7 watts. Okay. So once we have these two terms, right, we can directly substitute these two values into this particular equation. So we'll be having 10 minus 7 whole thing upon 1 plus e to the power of VIT divided by VT, right? And then what we can do is we can take factor 10 outside. If we factor 10 outside, so we'll be left with this particular term over here, that is 10 into 1 minus 0.7 volts. Remember, VCC is 10, so if we are taking 10 outside, so 10 divided by 10 is going to give us 1, right? Minus this minus sign remains as it is, and our I times RC value is 7 volts. So 7 divided by 10 is going to give us 0.7. Divide by 1 plus e to the power of VID divided by VT. So we get this particular equation over here, right? Then our VT value or the thermal voltage is basically equivalent to 25 millivolts. So 25 millivolts in fraction form is basically equivalent to 1 upon 40 volt, right? So keeping that in mind, if we substitute this 1 upon 40 into this particular equation over here, we'll be first simplifying this equation is just going to give us e to the power of VID divided by VT, right? Just simplifying this equation. Let's not substitute this, right? Yes. So directly simplifying this, right? Taking this numerator and making this term over here to have the same denominator as this one. We take this numerator and multiply it over here, and then simplifying this equation, we'll be left with 10, right? As it is, we bring that factor down. 10 into e to the power of VIT upon VT plus 0.3 volt, right? It will be plus 0.3 volt, right? So inside this bracket, it should be plus 0.3 volt. Whole thing divided by 1 plus e to the power VID divided by VT. Remember, this is one whole thing. So if we expand this particular formula, and if we in place of VT, we substitute 1 upon 40, it will become this particular term in place of VIT divided by VT. If we substitute 1 upon 40 in place of VT, that is going to give us 40 VIT. Okay, that is going to give us 40 VIT. So knowing that VID divided by VT is going to be 40 VIT and 40 VIT, right? And simplifying this particular formula, expanding this, so 10 times e to the power of 40 VID, so 10 times e to the power of 40 VID, and taking this 10 and multiplying with 0.3 is going to give us plus 3, right? Whole thing will be upon 1 plus e to the power VID upon VT. So this is the term that we get, right? Actually, this is the term. More clearly, this is the term, right? Okay. So basically, our V out is equal to this particular term over here. So you won't be able to prove for this. However, we'll be able to derive the V out equation, right? So we have derived the V out equation that we will be using, right? We will be using in our part C. In our part C question, right? Is this clear so far? How we derive this? Do you get it? Okay. So just in case if you are not able to get this, you can retry it, right? How we got this one. Moving on to part C of this particular question, it says by evaluating change in V out, divide by change in VID, right? Change in V out upon change in VID is basically equivalent to V out divided by differential input, isn't it? So that is going to be our gain. So change in V out upon change in VID at VID is equal to 0, determine the differential gain of the amplifier. Also calculate the differential resistance. So V out upon VID or differential input is going to give us the differential gain. So it says we have to determine the differential gain. So we know the formula of V out, right? And we have to differentiate it in terms of VID, right? So this is the equation that we got for VID, right? Over here. So let's just differentiate this term in terms of VID, right? Differentiating this whole term in terms of VID. So since I do not have proper tool to write it on screen, right? So what I'll do is I'll use a online calculator or online software to evaluate the equation, right? So in place of VID, we'll use VID. In place of VID, let's say we'll substitute it with X, right? So if we write this equation, so remember this 10. So what I'll do is I'll use a software. I'll use a program named Symbolab. You might be aware of um, this particular website, right? Symbolab basically evaluates your whatever mathematical solution you want, right? Um, so we'll just use that, right? You'll get a step by step solution for your solution for your question. So in place of VID, we are replacing it with X, right? So differentiating this whole term in terms of VID, right? So in place of VID, we'll use X. So let's write this whole equation in terms of X, right? In place of VID, we write it in terms of X. So that will be 10 e to the power of 40X plus 3 whole thing upon 1 plus e to the power of 40X, right? And we have to differentiate it in terms of X, right? Remember our X is equal to VID. So we have to differentiate this. So differentiating it, right? If you differentiate this, you'll get this particular term, right? So you can get all the steps over here, right? As it is. So some steps are logged, but however, it gives you the clear picture how to go about evaluating this, right? So the formula that you can use actually, or the rule that you can use actually to differentiate this particular term over here is the quotient rule, right? So using the quotient rule, you can get a solution for this particular question over here. So differentiating this, you'll get this particular term over here, right? That is 280. Let me half the screen. You can see both the screens. Let me cross this. Let me take you back. Sheldon, which screen can you see actually? At the moment, which screen are you seeing? Are you seeing the symbolic screen, or are you seeing my the handwriting one? The same one. So okay, you are not able to see this. You are basically seeing the slide, isn't it? The slide that I'm using for the solution. Okay, you are not able to see the symbolic solution, right? So let me just take that back. Can you see this solution now? Simulate solution. Okay. Okay, great. So what I have done is in place of VID, I have used X, right? For this particular software. So in this whole term will be 10 e to the power of 40x plus 3 holding upon 1 plus e to the power of 40x. Okay. So differentiate this in terms of VID. So if I replace VID and I use X as a representation, so whatever formula I have, I'll have to differentiate it in terms of X, right? So differentiating this, I'm going to use this Simulab named website, right? It actually evaluates your evaluate your questions, right? So whatever mathematical problem you have, you can use this particular software to check your solutions, right? So since I do not have the tablet or any sort of stylus to actually write it on screen, so this is why I'm using this particular program. Otherwise, I would have written this solution down directly, right? So this is what I get, right? So basically, I have written this particular equation in terms of x, right? In place of VID, I'm going to write it in terms of x. So I have to evaluate, I differentiate this whole term in terms of VID. So if I write it in terms of x, I have to differentiate it in terms of x. So differentiating this equation, right? You write the equation and differentiate it, you get this particular value, right? 280 e to the power 40 x upon 1 plus e to the power 40 x whole thing squared, right? And the rule that has been used is the quotient rule to find the derivation, right? So we get the derivation as 280 e to the power 40 x divided by 1 plus e to the power 40 x whole thing squared. Remember, our x is representation of VID, okay? So going back, once we have differentiated this, it says find the differential gain at VID is equal to 0. So what happens is once we have found the equation, the gain equation, this is the gain equation, right? So the solution is actually this one, that is 280 e to the power 40 VID, right? X is basically representing our VID. So 280 e to the power of this 40 VID divided by 1 plus e to the power 40 VID whole squared. So in place of x, since it says VID is equal to 0, so in place of x, we substitute 0. So substituting 0 in place of x and evaluating this whole thing, will get a gain of 70. So you can cross check, do you get 70 as your gain? Using this same formula, in place of x, we'll be substituting 0 because I'm using the substitution method where x is become, the notation x is basically representing my VID. So do you get that? The gain is 70. In place of x, substitute 0 and evaluate this. So you get the solution as 70. Okay, great. So your gain becomes 70 at VID is equal to 0. Okay. Next is to find the we are also supposed to calculate the input resistance. So our input resistance is basically given by 2 into beta plus 1 into RE, right? Small RE. So our small RE is basically given by VT divided by IE. Remember, since this particular circuit is symmetrical, this I value is equivalent to IE to IE, right? Isn't it? So half of this is my IE1, right? So basically in that particular case, our I value is 0.7. So half of that is basically equivalent to 0.35 million. So in that particular case, our RE is equal to 25 millivolt divided by, so this is my RE value, right? 25 millivolt divided by 0.35 milliamps, okay? So directly substituting this, right, our RE formula and knowing our beta value, that is 200. So we get substituting our values, right? So basically that is going to be equivalent to 2 into 201 because beta plus 1. So that is 200 plus 1. So that is 201 into our RE value, which is equal to VT, that is 25 millivolt, divided by our IE value, that is half of my I. So that is 0.35 milliamps. So our input resistance becomes 28.7 kilo ohms. Okay. So with that, do you have any queries or anything related to this week's tutorial? So with that, we finish off with the tutorial for this week. Okay. So do you have any queries for this week's tutorial? Okay, all good. So yeah, so we'll end this session over here, and have a nice weekend. Right. I'll see you. Since it's a long weekend, so have a good long weekend, and see you in next week's class. Right. Okay. Okay. Thank you.